So when we're talking about limits, so here are 3 examples of a function whose limit is this at infinity. We could look at, say, I think a little bit interesting. F of x, let's start off with the basic one. Let's think f of x equal to 1 over x, which we can totally graph, and I think it's worth graphing to see what these things look like. So that's what that function looks like. And we can see visually that as the x values get larger and larger and larger and larger and larger forever and ever, the corresponding y values get closer and closer to what number? To 0, right? Our y values definitely honing in on 0 there. Now you can also see this by looking at the function itself. In that fraction, if the denominator gets larger and larger and larger, the overall quotient is going to get smaller and smaller and smaller. You can even make a table if you wanted to. I feel like that's not really a good use of our time. But we can definitely see that the limit as x approaches infinity of 1 over x is indeed 0. Now, I want to really emphasize this notation, this sentence mathematically doesn't mean that this function necessarily ever has to equal 0. And it doesn't, right? 1 over x never actually equals 0. All this is saying is that this function gets as close to 0 as we want it to by making x as large as we need it to. That's the whole deal. I'm going to say it again. This function, you can make it as close to 0 as you want by making x as large as you want, as you need. And don't worry, I haven't forgotten about your question about the constant. We're gonna get into in a second. Let me show you another kind of, this example might be a little more atypical. Let's look at f of x equal to, sure, we'll do that one, cosine of x divided by x. And I will fully admit, I'm not great at drawing this one. So let's look at Desmos real quick, which I've hidden over here for myself like a smart person. Oh, is it over here? Yeah, okay, cool. So let's just do cosine of x divided by x. Oh, that looks terrible. I mean, that's not very interesting. That's because I've zoomed out weirdly, right? Cool. So we're not concerned with what's going on at 0, right? We're gonna be asking what's the limit. I know you can't see this, but we're gonna ask what's the limit as x goes to infinity. So if we scroll to the right here, well, look, it looks like it's getting really, really close to what number? 0. Now, I will point out there's a lot, infinite places where this function equals 0. So let me put this down for a second. The limit as x goes to infinity of cosine x over x is equal to 0. There's actually 2 things I want to point out about this. Thanks. Thing 1, the expression itself, not the limit. This does equal 0 whenever x is equal to pi over 2, or 3 pi over 2, or 5 pi over 2, or any odd multiple of pi over 2. And I want to really, really stress, it's okay for a limit to actually equal its limit value before you get, before you go all the way up. Or another way I can say this is, it's okay for a function to cross its horizontal asymptote. This function that I just stopped sharing, God, come on. That function there, which I know doesn't look very exciting over there, but that function definitely has a horizontal asymptote at y equals 0. When someone says horizontal asymptote, you can say, oh, that means when they take the limit as x goes to infinity, you get that number. So that's how you actually find a horizontal asymptote of a function, is you take the limit as x goes to infinity of that function, or negative infinity to the other side. And it's okay for a function to cross its horizontal asymptote. So again, mouse, this extended screen thing is challenging for me, clearly. So this limit is 0 because this function can get as close to 0 as we want it to, and we can x really, really large. Thanks. Sorry, I still not seeing the thing. Thanks. So the other thing I want to point out about this, because we might as well, how would you actually show this limit 0? I mean, I know we looked at the graph. You can see from the graph as you go way to the right, it's getting super, super duper extra close to 0. But if you actually wanted to prove on an exam that this limit was 0, you would use the squeeze theorem, or the sandwich theorem, as people call it. So the way you show this, and this is very, very typical when you're taking a limit specifically involving sine or cosine, and usually to infinity, although it doesn't have to be to infinity. So here's what I'm going to say. Cosine of x, this is something we all need to know, is always between what two numbers? What's the graph of cosine look like? What's the range of cosine look like? I think I heard some people say it when I was talking. It's always between -1 and 1. It's always true that cosine of anything could be cosine of x, could be cosine of x squared, could be cosine of 1 over x. Cosine of anything is always between -1 and 1. But then we can divide each of these things by the thing we need to make it look like the thing we're trying to take the limit of. So -1 over x is less than or equal to cosine of x over x is less than or equal to 1 over x. And then to apply the squeeze theorem, we take the limit of the two outer things and we pray that they're the same. If they're not the same, you don't get to use the squeeze theorem. So we're going to take the limit as x goes to infinity, and we can see, oh yeah, the limit as x goes to infinity of 1 over x is definitely 0. We did that one already. Similarly, the limit as x goes to infinity of -1 over x also has to be 0, which means the limit of this is 0, the limit of this is 0, this has to be between them, it's also 0. And that's by the squeeze theorem. Cool. Questions?
Because I know like the numerator is greater and the denominator is greater, that tells us
Tells us what?
like if it's going to infinity or 0.
Right. And so what I'll say about that comment, and we're going to explore that more, is that we generally only can really apply that rule when the numerator and the denominator are specifically polynomials, meaning you have nice positive integer powers of x and no other functions like cosine or sine or tangent or anything. So I will tell you all, if someone asked you to show this limit was 0, this is what they would expect you to do. No doubt about it, for sure. Unless they've specifically said something else, this is the work they're looking for. If they said find the limit as x goes to infinity of cosine x over x, 100% of the time. So there was a question about something like this. And this one I know is not the most exciting. What if f of x was equal to 3? Okay, well, this is where the language we often use with limits is maybe not excellent. Because the way I usually phrase something like this is, what is this function getting closer and closer and closer to as x gets larger and larger and larger? Well, that doesn't really sound right. Because as x gets larger and larger and larger and larger and larger and larger, what are the y values? Well, what are the y values? They're all 3. And they're not really getting closer to 3 because they're already at 3. So here's where we have to use the other language I mentioned, which is that it's not that necessarily that, I mean, we can get closer and closer. It's that if the limit is equal to whatever, 3 in this case, that means that you can make the function as close to 3 as you want by making x as large as you need. Well, in this particular case, it's already 3. So you actually don't have to do anything, right? It's already literally as close as it possibly can, because there's no distance between this function and its limit. So here it is still true that the limit as x approaches infinity of f of x is equal to the limit as x approaches infinity of the function 3. And the general way we say this is that the limit of a constant is always equal to that constant. And I know it's not very maybe satisfying, but that's really what's happening here. Is that we're just saying, oh yeah, the limit of this function, I can make the function as close to 3 as I need to by making x large. Well, it's already 3, so I'm done. Let's see where to go next. Oh yeah, let's do another. Yeah, let's talk a little bit more about the squeeze theorem because there's one more example I'd like to show you all, and then we can. In fact, it's a pretty classic example, and then we can talk more about more limits to infinity. So let's look at this f of x equal to let's do that one. X squared times sine of 1 over x, and I want to find the limit as x goes to 0 of x squared times sine of 1 over x, which I know is not a limit to infinity. But I will point out there's still kind of an infinity popping up here. Because 1 over 0 is problematic, right? If you plugged in the 0 for x, you get sine of 1 over 0. And sine does this. So if the insides of the sine function are getting larger and larger and larger, I don't know what the sine function is actually doing, right? It could be positive 1, it could be negative 1, it could be somewhere in between, but I don't get to say it's equal to or it has a limit that's one particular thing because I don't actually know. So when this inside part here is blowing up, we don't know what that's doing. Luckily, we don't need to. Actually, here's what I'll show you. If you just had that piece, I keep losing my mouse because I leave it over there. If you so if we look at just sine of 1 over x, let me zoom back to the regular zoom. Look what's happening as we get closer and closer to 0. You're getting a whole lot of oscillating, like an infinite number of times. So as this function, as x approaches 0 for this function, you would have an infinite number of oscillations. In fact, it is correct to say that the limit as x approaches 0 of sine of 1 over x does not exist. There's no one number that function is getting closer and closer and closer to as x gets closer and closer to 0. And we can see it, right? It's bouncing up and down forever, infinite number of times as you scrunch into 0. Luckily, that's not what we're being asked to prove. We're being asked to deal with this. And so here's what we're going to say. Like the cosine example we did. Oh, thanks. Yeah, good call. We're going to say that, all right, we know that sine of 1 over x has to be between -1 and 1. Definitely true. Sine of anything is always between -1 and 1. And then we want to take the limit of x squared times sine of 1 over x. So we're going to multiply everything by next x squared. You here for co-17a?
I was for like cheating or
You might be in 3218. It might be downstairs, but it's definitely, unless you're here for specifically math 17a, then this is not the place for you. So I'm multiplying everything by x squared. And so now here's what I've got. Negative x squared less than equal to x squared sine of 1 over x less than equal to x squared. And then what I'm really kind of doing is I'm just taking the limit of everything. You could really, if you don't, people don't usually write this next line, but it's totally not incorrect, or correct is also a way you can say that. That's right, the limit as x approaches 0 of negative x squared is less than or equal to the limit as x approaches 0 of x squared times sine of 1 over x is less than or equal to the limit as x approaches 0 of x squared. But what's the limit as x approaches 0 of negative x squared? Everybody. Oh, I know you guys know it. You just don't want to say any words. It's 0. As x gets closer to 0, negative x squared also gets closer to 0. All right, think about the graph of negative x squared. So really, all I'm really doing there, I'm just plugging in 0. Plugging in 0 for x, I'm getting negative 0 squared. And I know, and I've talked about this, we haven't talked about this really yet. When you're trying to evaluate a limit as x approaches a actual real number, not infinity, one of the things we try doing is just substituting in the value that x is approaching, called the direct substitution. So here we can actually just plug in 0 for x and get 0 squared, which is 0. And the same thing is true over here, which means this limit is bigger than or equal to 0 and less than or equal to 0. It has to be 0. There's no other choice. The limit as x goes to 0 of x squared times sine of 1 over x must equal 0. Let me show you the graph, because I mean, the graphs are cool and not easy to draw necessarily, but come on. So let me show you. Let me get the regular zoom here. So here are our upper bounds. This is the upper bounding function for the thing I haven't graphed yet. And here's my lower bounding function. And we tap on an x squared there. And let's zoom in a little bit. Check that out. See how the red function, x squared sine of 1 over x, is totally stuck between the blue and the green function? And how, since the blue function and the green function are both going to a y value of 0, the red function is getting smushed in between them also to a y value of 0. That's the whole squeeze theorem. If your function is stuck between two other functions and those two functions are getting close to the same value, it's got to be the same value. Oh, I forgot to put a picture up in the thing. Sorry for people on Zoom. I'll put a picture up in the thing. If that's the case, then the middle function also gets squeezed to that same value. That's it. We're stuck. We're happily stuck. That's what we want to happen. Sorry. Go ahead and let me give the people on. There we go. There I am for you on Zoom. Hello. All right. So let's look at some more limits to infinity, though, because I know that's what is kind of what's happening for people right now. So yeah, limits to infinity. Let's look at some examples. We want to evaluate some limits. I think the limit as x goes to infinity. Let's start with something fun, like 3x squared plus 1. Oh, no, let's do that instead. Yeah, that's smarter. Over x squared plus 2. Whoops, you can't see that quite all the way. So you might already know what this limit is, but I want to show you something. Really, I want to show you that you can do some simplifying here. Meaning, what do I really want to show you? You can plug in some values, but I really want to say, like, you could totally make a table, and if x is 1, that's kind of boring. Y is going to be 3 plus 1 over 1 plus 32, so you get 4/3. And if x is 10, you're going to get like 301 over 102. And already you might be able to see, well, this is pretty, 301 divided by 102 is pretty close to what? To what whole number? What's 300 divided by 100? 3. So 301 divided by 102 is pretty close to 3. And if we go bigger, like 100 squared is 10,000. So I got 30,001 divided by 10,002, which is even closer to 3. It's not exactly 3, right? This top part would need to be just a little bit bigger. It's just a tiny bit smaller than 3. So is that one there. But all these numbers are getting closer and closer and closer to 3. Yeah.
Can we also just see it by how the numerator and denominator both have power of 2? We could just divide.
Right. So there's a shortcut that we're going to talk about in just a second, which is that if the degree on top and the degree on the bottom are the same, then the limit as x goes to infinity is the fraction or quotient of the leading coefficients. However, if your teacher wants you to show the work for this, here's the work I would recommend doing. You're going to divide or factor out x to the highest power in the denominator. So here, the highest power of x in the denominator is x squared. You can either do it this way. You can say it's the limit as x goes to infinity and literally divide everything by x squared. That's one way to go. And then we can simplify that. And that's the limit as x goes to infinity of x squared over x squared cancels, you get a 3. Oh, sorry. Yes, of course. And then x squared over x squared, there is a 1, and you have a 2 over x squared. So let me ask everybody, as x goes to infinity, what happens to 1 divided by x squared? Does it get big or does it get small? It's very small, right? Because you're having a huge denominator. This is going to approach 0. And the same thing is true for 2 over x squared. As x gets very large, that portion becomes insignificant, negligible, not important. So what are we left with? 3 over 1, which is 3. I will mention you should write the limit in every step until you're actually getting a numerical value. And if there are still variables in your expression, you should still be writing the limits. But once we get just numbers, you don't write the limit anymore. Because this is really asking the question, what is this thing getting close to as x gets big? And if you don't write that, it doesn't mean that anymore. The other way you can do this is instead of dividing everything by x squared, you can essentially still divide everything by x squared, but other people like to factor out the x squared and say, okay, it's x squared times 3 plus 1 over x squared over x squared times 1 plus 2 over x squared. It's literally the same work because you're going to cancel those x squared, and then this is still going to go to 0. This is still going to go to 0, and you're going to get 3 plus 0 over 1 plus 0, which is 3. This is just a difference of, I don't know. I mean, it's not really a difference at all. The plus 3. I'm not sure which plus 3 you're referring to.
Like 3 plus.
Well, so I want to point out this 3 is that 3. Can we ignore that 3? We can't, right? I'm just trying to show you all kind of, so I know that we kind of ignore maybe constants, but this is how someone would expect you to show that this limit actually was what it was, right? I know that we have a nice little trick for doing it when the powers are the same, but this is the work behind that. This is why it works, right? Because if the highest powers are the same, then when you divide everything by that highest power, every other term ends up being divided by some power of x. And that's going to make all of those get infinitesimally small as x gets infinitely large. But you're right. I would totally, if I was just doing the work and not maybe writing solutions to an exam, if someone asked me, hey, James, what's the limit as x goes to negative infinity of, 5x cubed plus 3x plus 2 over 7x cubed plus 4x squared minus 9, we would all say that this limit is equal to what fraction? 5/7, right? The degree on top and the degree on the bottom are both 3. So the limit to infinity or to negative infinity, as long as it's a nice rational function like this, the limit's always going to be the quotient of the leading coefficients. So it is not incorrect to say, we know that's 5/7. Now, I should really stress, you only really can use that shortcut. Well, one, if your teacher says it's okay on the test, if you're taking it. But 2, it only is genuinely true if your functions are rational functions, meaning it's a polynomial on the top, positive integer powers of x, it's a polynomial on the bottom. Doesn't work if you got other things in there like square roots or sines or e to the x's or anything like that. Although there is a way to deal, there is a similar-ish rule for things when you have like e to the x's or 2 to the x's. So we could talk about that too.
Square roots of like
Right. So yes. And what I'll say about this is you can kind of, well, as long as you're in the domain, you can treat powers of x like rational functions. So I will backtrack that a little bit. It would be really okay to apply this kind of rule to anything where you have just nice positive powers of x. Negative, no, you probably any powers of x would probably be fine. As long as you, can see this. So again, if I were showing work here though, I would write this as the limit as x goes to negative infinity and I would divide every term by x to the third. The highest power of x in the denominator. I know they're the same here, but we want to stress the in the denominator part because when they're not the same, you need to be careful. It's much easier to deal with the highest power in the denominator than the numerator. So we get, so I'm going to do the work quickly here. 5x cubed over x cubed is 5. 3x divided by x cubed is 3 divided by x squared. 2 over x cubed. And in the denominator, I get 7. I get 4 over x. I get 9 over x squared. Now, as x gets infinitely large, what happens to all of these pieces? They go to 0, right? 3 divided by infinity squared is really super small. So are all the other things. So this limit ends up equaling 5 plus 0 plus 0 over 7 plus 0 plus 0. Like we said it was before we did the problem. I'm just showing you the work because I think it's not like you have to see this work, but I think it's worth seeing.
For the denominator, isn't it supposed to be x to the power 3?
So I didn't show the work for the intermediate step. Here's the work I'm not showing. I took my expression and I divided each thing by x to the third. So I have 5x to the third. Oh, you mean this term right here?
Yeah.
Sorry, I apologize. My 2 just looked terrible there. It's a 3. Yeah, sorry. Yeah, you're right. I thought you were saying something totally different. Yeah. A good, other than that, tiny mistake there. So we also have, so I actually could say there's a rule 1. You take the limit as x goes to either positive or negative infinity, and you have some polynomial divided by some other polynomial. This is equal to, I'm going to write something and then we're going to say something about it. It's equal to a sub n over b sub n, where the polynomial p of x is a sub n times x to the nth power plus lower powers of x. And similarly, q of x is b sub n times x to the n plus b sub n minus 1 times x to the n minus 1 plus lower powers of x. So, right, the leading coefficient here is a sub n, and the leading coefficient here is b sub n. And those highest powers are the same, which means the limit is equal to the fraction of the leading terms, or the leading, actually, I should say the leading coefficients, which is this divided by this. That's a lot of writing to say something that we already said. But that's kind of how people usually write it in a textbook. It's like, oh yeah, we say this thing. So that's one rule we have. If the degrees are the same, the limit is equal to the leading coefficient on the top divided by the leading coefficient on the bottom. What if the degrees aren't the same? What if we had something like the limit as x approaches infinity of 3x squared plus 1 over 2x to the 4th plus 9x minus 5? Now what's going to happen? Well, let's think about it for a second. Which of those polynomials grows larger faster? The one that's squared or the one that's to the 4th? Right, the 4th one, the higher power gets bigger faster. If you plugged in 10, 10 squared is only 100, 10 to the 4th is 10,000. So the bottom is clearly growing faster than the numerator, which means the overall quotient is getting big or small. If the denominator is big or bigger than the numerator, the overall fraction is going to be small. And that's always true, right? Bigger denominator, smaller fraction, bigger numerator, larger fraction. So this is, we know already, we're pretty sure this is getting small. Now, one time, actually quite a while ago now, a student showed me a trick they like to use, which I thought was really clever. It only works if the degree on top is less. He said, well, James, you really have the same degree on top and the bottom. You have a 0x to the 4th plus a 3x squared plus a 1 over a 2x to the 4th plus a 9x minus a 5. I was like, oh, that's clever. Because then the degrees are the same. And what's the quotient of the leading coefficients here? 0 divided by 2, which is equal to? Right. That's kind of a tricky way of doing it. It is correct though. But now let me show you the work. So the work I would do to show this limit is actually equal what it's equal to is I would divide everything by x to what power? Sorry, I didn't hear what you said. Right, the highest power of x in the denominator. So I'm going to rewrite this as, I'm going to do the work right this time. 3x squared over x to the fourth is 3 divided by x squared. 1 over x to the fourth. And the denominator, 2x to the fourth over x to the fourth is 2. 9x over x to the fourth is 9 divided by x cubed minus 5 over x to the fourth. And just like every other time, when things are divided by x to a power and x is getting large, they're going to 0. So this is going to equal 0 plus 0 over 2 plus 0 minus 0, which is 0. Generally, for the limit as x goes to either positive or negative infinity of p of x over q of x, I'm going to write this one nicer. If the degree of p is less than the degree of q, then the limit's equal to 0. Which makes sense, right? The bottom is growing faster than the top. So the overall fraction is getting smaller and smaller and smaller. Okay, the last case is kind of the worst case. I should also point out, right, this rule totally applies for like the limit as x goes to infinity. Sorry, you guys can't see that. Limit as x goes to infinity of 1 over x. That's definitely a rational function where the degree on top is less than the degree on the bottom. What's the degree of the polynomial on the bottom? What's the degree of the polynomial on the top? That many, right? There's no x's, so you've got x to the 0. So a constant is a 0 degree polynomial. So a constant is a polynomial. So yeah, this is also 0. But we already knew it was 0 here. Okay, the last rule. Well, not the last rule, like the next rule. What if we wanted to find the limit as x goes to infinity of, let's make it interesting here, 2x cubed minus, yeah, all right, x to the fourth plus x all over. Sorry, I'm trying to make this problem not terrible. Let's do that. Let's do x squared plus x minus 1. All right, that looks awful. So first of all, someone did a bad job of writing this problem because they should have written the negative x to the fourth first, right? We should definitely write our polynomials and our rational functions in kind of the standard way, where the highest power term is first, and we write things in descending order. So for this particular problem, the numerator is definitely getting larger faster. So we would expect to have some fraction that is getting very, very large, or possibly very, very negatively large, depending on what's happening. So let's go ahead and do the thing that I think we should do, which is we're going to divide everything by the highest power of x in the denominator. If you divide everything by x to the fourth, things get weird here. If you divide everything by x to the fourth, you end up getting like 1 over 0. And it's unclear if your answer is going to be a really, really large positive number or a really, really large negative number if you divide everything by the highest power of the numerator. So let's be more careful. The limit as x goes to infinity, divide everything by x squared. So I'm going to get negative x to the fourth over x squared plus 2x cubed over x squared plus x over x squared divided by x squared over x squared plus x over x squared minus 1 over x squared. And here's where I'm going to encourage you to be a little extra careful. We know that these things are going to go to 0, but you really shouldn't. So here's what I don't want to write. I don't want to write this, even though I'm going to write it. I'm writing it in green because I don't like it. Not that I don't like green. Green's a great color. I don't want to write this. I know all the other things go to 0, but the problem is, kind of the issue here is that when you're evaluating a limit, you kind of have to evaluate it all at once. Meaning it's less okay to say that this is just that, because they've kind of dealt with part of it, but not with all of it. So what I would rather have you do instead is think about everything that's happening. So these are going to go to 0. And what's this going to do? What's negative x squared going to do? Is it going to be negatively big or positively big? So let me ask you guys a question. If you put in a number for x, would you square it first or make it a minus first? Square it first. So like if I put in 3, I'd have 3 squared, but then negative 3 squared. So if I put in positive infinity, I'm going to square it, get a bigger infinity, but then it's going to be the negative of that. So it's going to be a negative infinity. Plus double infinity. Uh-oh. I've got negative infinity plus infinity. Which one's bigger? It's not always easy to tell. In this case, it is easy to tell. The negative x squared is definitely a quote unquote bigger infinity than the 2x. But if you don't like that, I don't like it. Here's a way around it. From negative x squared plus 2x, factor out an x. This might be more work than your teacher would really require. So now let me ask you, all these things still go into 0. Where is x going to? Infinity. Where's negative x plus 2 going to? And what's infinity times negative infinity? Negative infinity. So this one's going to negative infinity. You can totally reasonably say the negative x squared is more negatively infinite than the positive 2x is positively infinite. But this is a more precise way of showing that it's actually negative infinity. So very generally, if you have the limit as x goes to either plus or negative infinity of p of x over q of x, if the degree of p is greater than the degree of q, then the limit will be some sort of infinity. But it really requires greater inspection than just saying it's a this or that.
Why is 1 in the denominator?
Oh, because that's sorry, that is an excellent question. Yeah. Because we actually want it to be 1, not 0. Apologies, yeah. So we end up with negative infinity plus 0 over 1. And that's negative infinity. We really would prefer not to be divided by 0 there. So yeah, excellent question, good observation. Yeah, sorry. Yeah.
When you say it goes to like negative infinity, what does the graph look like?
Oh, what does the graph look like? Excellent question. I have no idea. Luckily, we have tools. So let's actually take a look at this graph. I'm curious to see what this graph looks like. So let's see here. What have we got? Some bonkers thing here. We've got y equal to 2x cubed. I like to do the division now. And then you like it. So, yeah, okay. Come on, don't be like that. On the bottom, we have x squared plus x minus 1. Numerator we have. Oh, I had the minus x to the 4th first. Sorry. And then we had a plus x. I want to. Okay, so not very helpful there. Let's zoom out a bit. Oh, okay. So you can see, hopefully, that as our x values go to the right, can we see? Oh yeah, the y values are going to get super negative. All right, so as x goes to positive infinity, the y values go down, 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 down. And as x goes to negative infinity, the y values get positively large. So it is also true for this problem that if you were asked the limit as x goes to negative infinity, of 2x cubed minus, sorry, I should write it the other way, minus x to the fourth plus x over x squared plus x minus 1. Okay, here's what I'm really doing. If I was trying to do this the short way, here's what I'm actually thinking about. I'm still going to show you the long way, but I'm really thinking about, this is essentially, I only really care about the highest powers. The other stuff is garbage. This 2x cubed is meaningless in the face of this x to the fourth. This x and this 1 are meaningless in the face of x squared. The x squared is always going to overpower them. So the leading term decides what the thing looks like. Sorry, the leading terms decide what the thing looks like. So this is essentially negative x to the fourth over x squared, which is essentially negative x squared. And if x goes to, sorry, my brain just, yeah, that's right. Interesting, we're gonna have to do some more exploring here. Because looking at this, if you square the negative infinity, you get infinity, but then the negative in front of it makes it negative infinity. So I would guess, I feel like I might be wrong, but I would guess that this limit is negative infinity. Let's find out, and then we'll go back and look at the work. Well, we can actually not do all the work again. Let's be smart and copy our work from up here. So that's going to be the limit as x goes to minus infinity of x times negative x plus 2 plus 1 over x over 1, which doesn't go to 0, plus 1 over x minus 1 over x squared. So this goes away, this goes away, this goes away, and negative infinity times positive infinity gives us a negative infinity. So this limit should also be negative infinity on the left. So let's go back and look at our graph. All right. It definitely doesn't look like what's going on over there. What's up with that? Do we need to zoom out further? There we go. We got fooled by the graph. So if you go further to the left, you can see, oh, actually the y values are going to go down to negative infinity. So if you're ever using a graph to kind of explore what a function looks like, don't limit yourself, right? I clearly was like, oh, it's positive infinity because right? It definitely looked like it got super, it does get super big. But then if you go far enough out for the x values, what's probably happening there is that in this small region from 0 to whatever, the x cubed is maybe, the 2x cubed is maybe a little more powerful than the x to the fourth, and so it's overcoming it. Or we're dividing by something that's negative and so it's making it positive. Either thing can be happening there. So yeah, don't get fooled by graphs. The time just flies by. So, couple other, might as well spend the last 5 minutes of class continuing to talk about limits to infinity. Sure. Let's talk about, oh yeah, that's a good one. Let's talk about something like this. The limit as x goes to, I'm just going to go with the negative infinity here, of a square root of x squared plus 6x over, let's make it fun. Sorry, 4x, it doesn't really matter, plus 3. This is one that's annoying. I will point out, if I was looking at this, I would say to myself, well, I don't have polynomial on the top, right? The square root makes it not a polynomial. I can write it all in the 1/2, it's not super helpful. But what I would observe is, although it's not exactly what I have, the biggest thing on the top is the square root of x squared, which is kind of like x. And the biggest thing on the bottom is also x. So my highest powers, in quotes, are both x to the 1 on top and x to the 1 on the bottom. That's not exactly true, but it's true enough for me to work with. So here's what we're going to try to do. We're going to try to pull out an x somehow from the top so we can cancel it with an x on the bottom. What we really want to do, but we can't do yet, what we would like to do is divide everything, top and bottom, by x. But to really be able to do that, you have to be able to pull an x out of the square root. Well, we can totally do that. Watch this. I'm going to rewrite the square root of x squared plus 6x as the square root of x squared times what's left after I factor out an x squared from x squared plus 6x. 1 plus what? It goes there. Exactly. And the bottom, still boring 4x plus 3. Okay, now here's a hard question to answer. It may sound like an easy question, but the answer that's easy is not the right answer. What's the square root of x squared? It's not just x. I think I heard someone say the thing that's almost right. I'm going to write this first. I'm going to break the square root up into 2 pieces. And now the square root of x squared. So let me, I feel like I might have said this in this class before, but I don't remember. I might have said it in my other class. So let me just ask you 2 quick questions. What's the square root of 5 squared? Not a trick. Yeah. This one's slightly trickier. What's the square root of negative 5 squared? Still 5, right? So the square root of x squared is x, but the square root of this x squared is not x. It's the opposite or negative of x. There's another function that does this. It's called the absolute value. So the square root of x squared is not kind of, but it is exactly the absolute value of x every single time. So we can replace this with the limit as x goes to minus infinity of the absolute value of x times the square root of 1 plus 6 over x over 4x plus 3. All right, so here's the deal with absolute values. The absolute value of x gets to be x if x is positive, but it gets to be negative x if x is negative. Right, if x is negative 5, the absolute value of negative 5 is negative 5. So in this limit, is x negative or positive? Negative, right? Since x is going to the most negative place it can, x has to be negative. So for this limit, we're going to write that this is the limit as x goes to negative infinity of negative x times the square root of 1 plus 6 over x over 4x plus 3. Because x is a negative number and the absolute value of a negative number is the negative of that number. Sorry, get too excited there. On the other hand, if this limit had been as x goes to positive infinity, the absolute value of x would have transformed into just x. You wouldn't have the negative sign there. So it's a different limit based on whether you're going to negative or positive infinity. Now we can do the thing that we wanted to do. We can divide the top and bottom by x. If you got to go, you got to go. I'm just going to finish this up. So we can divide everything by x. On top, we get the square root of 1 plus 6 over x. On the bottom, we get 4 plus 3 over x. And then all the things being divided by x go to 0. Oh, I forgot the negative sign. That's not important. That is important. And then we get negative 1 over 4. And just for context, if it was the limit as x goes to positive infinity, your answer would have been positive 1 over 4 because we wouldn't have had that negative there. Question?
What did you put in x?
So, I will admit, I skipped a little step there. So the step I'm skipping there is dividing the top and bottom completely by x. So really from here, what I'm doing is I'm writing this as the limit as x goes to negative infinity of the entire numerator divided by x over the entire denominator divided by x. But then this divided by x, the x's just cancel, and you get the limit as x goes to minus infinity of negative square root of 1 plus 6 over x. And here we divide each thing by x, and 4x over x is 4, and 3 over x is 3 over x. That's happening there.